Hello and welcome back to this 38th lecture on biomicroelectromechanical systems. Let us quickly preview what we did last time. We talked about thermal oxidation mechanisms, particularly Deal-Grove kind of modeling systems where wet and dry oxides could be possible thermally on at the expense of consuming silicon from a surface, and it is a diffusion driven process. We talked about some polymer MEMS and partly covered different techniques like soft lithography approaches, compression molding, inkjet printing, so on and so forth. We started with replication and bonding processes and then molding processes, and then basically investigated what kind of wafer bonding schemes are really available, and for plasma or for polymer related processes or polymer MEMS we use this very commonly available technique for surface modification or energy wherein a surface is actually brought to a high energy from a lower energy by exposing it to gas plasmas. So in this context we were evaluating some of the plasma systems and processes, and we started with a DC glow discharge, talking about how plasma can be formulated, how it can be used towards machining, and we found out the mechanisms where a diatomic gas would actually ionize or excite and create different kind of free radicals, ions, electrons, other species, so on and so forth. And then we also found out that we can actually drive in these ions onto a substrate which are kept on the cathodic side or the Crookes dark space to do fabrication. The substrate nature sometimes being insulating in case of polymers may extinguish the plasma which is otherwise a self sustaining process, and so therefore we need an RF frequency sometimes to actuate the polymer mechanisms. So we talked about RF discharges and the way they are made, and also discussed briefly about what is an impedance matching network. If you may remember, we need to use the maximum power transfer theorem for ensuring that the power which is pumped out of the RF generator is 100% coupled to the system, and for proper power coupling it is important that the impedance of the system, plasma system, is same as the impedance of the source resistance or impedance. And for the very fact that the plasma system being a non-homogeneous material with different dielectric constants, you never know how the impedance would vary, and therefore you have to always have some kind of a matching network in series so that the overall impedance can actually be made equal to the source resistance, so that you could pump out maximum power from it without getting things reflecting off at the source resistance end. Okay. So now let us look at how this RF plasma is created and generated and sustained, okay, and what are the basic differences in this case than the earlier used DC glow discharges. So as I told you before, this blocking capacitor ensures that the RF source 100% feeds the voltage supply onto this parallel plate system, and here you have these ions and electrons as you are seeing, species which are made within the plasma chamber. Now if you actually go ahead and produce or couple the RF source onto the plates, there is almost always a change in polarity with the RF signal. So for half cycles this plate may be positive and this may be negative, and for the other half of the cycle this may be the opposite behavior. So assuming for the first half cycle you will have the ions moving downwards, okay, and the electrons going upwards because the anode is up here, and the next half cycle exactly this other sequence will be repeated because now this will be the negative end and this will be positive end, and so the positive ions would go towards the negative plate and electron opposite. And so really as the frequencies kind of switch, you have the ions and electrons kind of alternating between the two plates, as you can see in this particular illustration, okay. And one more important factor is that beyond a certain frequency which is typically about 10 kilohertz or so, the behavior of the ions change slightly. Below 10 kilohertz it is almost always that the ions and electrons move parallelly and they go towards the opposite plate, and as you change the polarity they would also change the direction of their motion. But above 10 kilohertz the field is too fast for the heavily moving ions to follow the field, as a result of which it is only the electrons which go around and ions kind of remain static within the bulk of the plasma, and due to which sometimes the plasma plates in such an RF discharge at above a certain frequency above 10 kilohertz attain negative charge in comparison to the bulk of the plasma, which is otherwise positive because of the accumulation of the ionic species within the bulk of the plasma. So, RF systems typically have Crookes-Stark spaces in both the areas, both the plates, okay, and essentially the problem of polymers or insulating materials being exposed and the plasma self sustenance not able to happen is kind of taken care of by mechanisms wherein the other plate which is not covered by the insulating material is used as an electron generation mechanism, and because both the plates are negatively charged with respect to the bulk of the plasma. So, that is what radio frequency discharge really is, and as you see here in the frequency range above 10 kilohertz, only the electrons are the one species which move and the ions remain stationary. Let us now look into another aspect of how plasma can be created, and that is essentially magnetically enhanced plasma systems. Another mechanism of producing these plasmas, particularly high density plasmas, is also the magnetically enhanced plasma systems, as you can see here. Okay, in this particular plasma system, and essentially inductively, we also call it inductive coupling of the plasma in this particular behavior. Mostly this is used for the bonding mechanisms within 2 or more wafers where surface energy is used. So, either RF frequency is used or magnetically enhanced plasma systems are used for this kind of bonding mechanisms. So, we call it inductively coupled plasma, okay. And the way this system works is very unique and simple. So, there is a coil as you are seeing here, which is placed around the chamber, okay, containing the gaseous species. So, this coil is actually the RF coil and it has a radio frequency, and let us suppose that we have at one point of time a current across this coil which goes in this direction. So, as if with using the right hand grip rule, if the coil kind of the current goes in this clockwise sense, the magnetic field will be pointing downwards, okay, and then if the current is reversed back, the magnetic field should be pointing towards the direction of the thumb, that is upwards. So, you have a bidirectional magnetic field frequently oscillating in the plasma system just by coupling this current across the coil around this plasma chamber here, which has the gaseous species in it. The gaseous species is flown in typically and flown out, okay. Now, there is a flow out mechanism, let us say in this particular area, and you create a constant pressure and a constant flow rate of a certain diatomic gas, and essentially what you do is you first now create through a Tesla coil, which is actually placed here, a small spark which excites a few atoms and makes them ions and electrons around the coil area. So, now you have highly moving or high velocity ions and electrons which have suddenly come out of the localized domain where the Tesla coil had given its one firing and essentially or sparking, and therefore, these ions and electrons can be further driven by using Lorentz forces by the magnetic fields which are kind of coupled. Okay, so, a Tesla coil on the top of the chamber is activated, causes an electrical discharge. This discharge causes some gas atoms to dissociate and come to excited states, also generate ions and electrons, and finally these ions and electrons are moved around by means of this coupling magnetic field. So, as I told you, if the current is in the clockwise sense, the magnetic field is in the downward direction, as you can see here in this particular illustration. This is the magnetic field's direction, and this being the direction of the current across, and so therefore, this magnetic field is able to cause both the ions and electrons to experience forces, and these forces are Lorentz forces, which are also given by F equal to QB cross V, where B is basically the magnetic field, V is the velocity of the moving ion, and Q is the charge on the moving ion or the charge species, which may be an electron. So, we can really balance this force, as you can see here, in a manner so that you can equate this to the centrifugal forces or the centripetal forces mv square by r of an ionic system. Okay. So, we are talking about a situation wherein we are balancing the magnetic force, the Lorentz force Fb with respect to the centrifugal force on charged species, and we are letting them to execute circular motion, as you can see, of different radii here. Okay. So, there are different circular motions that are generated from different species, and essentially the r vector here is nothing but mv by qb. Okay. This is equal to qvb, assuming that the v and b are always perpendicular to each other and sin 90 is 1. We can actually make the magnetic field, or the way that the Tesla fires the charge into the medium, be always perpendicular to the direction of the magnetic field. And so therefore, essentially the idea is that the radius of motion that will be generated in that case will be simply mv by qb. So, this is the mass per unit charge, and this is the velocity per unit the magnetic field, and we can really create this kind of a condition by placing the Tesla coil and the magnetic field's value in a manner that you have ions to move along in radii, small radii. Now, I would like to bring to your notice one important thing, that the ions are very heavy in this particular case, and therefore they would execute larger radii from this particular equation, whereas electrons are not so heavy, they are comparatively much lighter, and they would be executing much smaller radii, and this kind of makes an ion or a diatomic species dragged along with the ion to collide with multiple electrons as these small circles and big circles intersect. Okay, the small circular path of the electron and the big circular path of the big heavier ion intersects, and that causes higher and higher density of the plasma system. So, you have more electrons, more ionization which is generated, and then we can actually keep on building the energy this way, so that you can have a localized high density plasma system. So, inductively coupled plasma really produces a lot of situations where the density attainable of the gas plasma is probably the highest. Okay, and that is how these kind of plasma systems operate. So, let us look at into a very practical example of such a inductively coupled plasma system, also known as Trian inductively coupled plasma system. Trian is the name of a company, it is based in Dallas, Texas, and essentially they are using they are making these clusters with 5 or more chambers of inductively coupled plasma chambers, whose cross section has been illustrated here. So, as you can see here, there is this gas chamber which is actually evacuated using a set of turbo pumps to a very low active or to a very high vacuum level, and then there is a gas flow maintained inside at certain flow rate in terms of SCCM, standard cubic centimeter per meter, and process inlet gas typically goes from this direction, and there is always a catch to how the process inlet can be sent in, and I am going to illustrate that in a little bit. This is the ICP coil. As you can see, these coils are actually placed around the chamber and is used for generating magnetic field. This is a viewport window through which you can see whether the plasma has been created. This is the chamber block which is used, which is perforated, and there is a cooling mechanism which would give continuous cooling to the metal of this particular plasma, and then there is a vacuum port here and helium coolant inlet which actually tries to go and take off the heat from the metal. Plasma, again, mind you, is a high radiation intensive process, and metal containers may get heated up with that radiation. So, you need active cooling effectively, and essentially there is a RIE matching network somewhere at the bottom here which would be able to give maximum power transfer from the RF generator onto the plasma system once the plasma system has been created using magnetically enhanced plasma mechanisms. In this case, the plasma, I like to recall, the plasma is created using coupling magnetic fields, but the plasma can be driven using RF, and so therefore this can be also effectively used as exposing insulating surfaces, which is normally done by using an RF bias to such systems. So, one problem here though which is very important is the fact that you have to somehow introduce velocity in the flowing ions or species, so that the term B cross V really gets effective. Okay, and there is a finite amount of force which is generated because of that. So, in order to do that, you create two capillaries of or streams of air. One stream, as you are seeing, is going in this direction, there is an outer gas. which kind of revolves here throughout the chamber and goes into this main chamber, and then there is an inner gas which goes from the inlet stream, and then they kind of mix and creates a lot of turbulence in this particular zone, which causes the mixture of inner and outer gases to generate even a denser plasma. So as V is more, the turbulence factor is more, local turbulence is more, and there is always a tendency of more and more collisions between the ions and the electrons based on theories formulated earlier. And so these flow rates can be controlled in a manner so that the inlet process gas results in some kind of a density of states of the plasma system. So the figure on the left here shows a schematic of the gas piping that leads the process gases into the chamber. Two streams of gases are injected. One is the inner stream, that is the main process gas, and then there is a secondary stream shot at an angle. It is mainly used to produce turbulence in the plasma chamber, as the molecules in secondary stream have higher velocities and are directed at an angle. And the plasma is produced in the same way as mentioned in the previous slides, and much denser system can be produced by changing the velocities of the secondary and the primary streams and mixing and matching as is applicable. The addition in this case is the application of an RF bias, which actually typically drives the plasma to go work on the substrate, as you can imagine in this particular case. So having said that, let us see what plasma processes can really do. So basically the plasma, the gas, one of the purposes of plasma is to etch surfaces, and essentially if you look at the definition of etching, it is really as I have been illustrating before, it is an act of engraving in which an agent eats away lines or surfaces left unprotected in different substrates. Okay. So here also just analogous to what happens in the wet etching case, there is an undercut problem. So if you have a masking layer like this, as you are seeing here, there is a tendency of the whole profile to kind of eat away into the masking layer, as you can say, in both these directions, and so therefore the overall opening size is more than the opening provided by the mask. So that is actually undercut, and the extent of undercut is again given by this formulation here, and essentially it is known as the mathematical term H anisotropy. Okay. So the anisotropy of an H is essentially 1 minus the lateral H divided by the vertical H, RL by RV, and if A is 1, it means that RL and RV, RL is the lateral H is 0, and so the channel is perfectly straight faced, which happens normally in dry and other mechanisms. And if the lateral H is equal to the vertical H, the anisotropy is 0, which means that it is a perfectly isotropic H. Okay. So therefore the lateral H rate is pretty much similar to what the vertical H rate is, and you end up into getting some kind of a hemisphere of etching. Now based on the different pressures that the plasma formulated, the gas plasma is formulated in, you can divide into different etching regimes. One where if the pressure is too high and the mean free path is too low, you call this just a surface based high pressure plasma etching, which causes a surface place modification, the chemical modification of a small atomic layer on the surface. You go a little bit lower on the pressure, let us say from 10 to the power 3 to 10 to the power 1 torr, all the way to about 10 to the power minus 1 torr to 10 to the power minus 3 torrs. And so in this particular pressure regime, again you have another technique, reactive ion etching, which I have described in details before during microfabrication processes. Here there is a removal mechanism and also there is a chemical change, both followed. So it is a physico-chemical process of etching. If you go further down on the pressure to as low as about 10 to the power minus 3 to minus 5 torrs, you get what you call ion milling. It is simply ablation of material, mechanical removal, wherein the plasma is high enough, plasma has a high enough impact to cause the material to get degraded or ablated off the surface. That is called ion milling. So you have 3 different regimes of plasma etching based on what are the operating pressures that somebody would have. Okay. So the lateral H again is the amount of H in the direction in the lateral direction. So, here for instance this is the vertical direction of the etching and this is the lateral direction of the etching in both directions. Okay. So, essentially 0 lateral etch is something which can be represented by this kind of a trench. You can see the mask and the layer below it are more or less same. If you have a positive lateral etch, you have almost an undercut below the masking or the sacrificial layer. You start with this, which is by depositing some kind of a resist mask or a sacrificial layer on the top here. So, if you want to avoid this problem, you can actually use low pressure plasma regime, wherein the ions have sufficient momentum and direction to cause vertical etches, okay, or vertical structures etched through the photoresist mask, so thus causing 0 lateral etch rate. So, let us look into another aspect of plasma etching and how we can have different steps or different ways of this whole etching process. So, really it is all about generation of positive ions or electrons or free radicals, which are represented by this high energy state here, okay, of materials that a plasma system really comprises of. Now, you will basically keep the substrate somewhere here and put a site bias voltage also, so that these ions hit the substrate with certain momentum, and also the free radicals go towards the particular substrate. So, the way it would happen is that one of the free radicals suddenly goes all the way down from this chamber atmosphere and sits on over the surface atoms. Let us say these dots here are the surface atoms, and the free radical kind of rolls and tries to find out an atom where it can really form some kind of a chemical bond with. Okay. So, the free radical is a high energy species, it looks for its partner, which is essentially a dangling bond on the surface, which may have been left over because of some other ionic impact which has been a preceding process from this process of free radical movement on the surface. So, you get a conjugate or create a conjugate, there is a chemical reaction which happens between the two, and this is one integral species now, and this can be taken away easily into the atmosphere and can be pumped out of the system. So, the way that you remove surface atoms really is based on 4 process steps. So, 5 process steps rather. You generate the free radical within the plasma, and the free radical absorbs onto the surface, number 2. Number 3 is the free radical kind of rolls over the surface to find out dangling bonds or sites or active sites where it can form some kind of a coupling or a reaction. Once the site is approached, number 5, in step number 4, it forms a chemical reaction. So, the free radical actually develops some kind of a compound species with the metal atom of the surface, thus reducing it or thus removing it from its interstitial site, and in the 5th step it gets carried away into the atmosphere as a gaseous species, which is now sent out of the vacuum chamber from the outlet side. So, thus you can have atoms of the surface etched off using this chemical reaction of the free radical, and it can be used for material removal, substantial material removal. You could mask the layer to prevent erosion over all the surface and to direct the erosion only on specific areas of the surface, and thus you can develop features and structures using this particular methodology. So, having said that, let us look at some of the results and discuss what really happens in case of the high pressure etching regime. As you know, we had started this topic or started this discussion primarily because we wanted to bond between 2 surfaces which were essentially polymers in nature, and as we said that we use a clean bonding protocol using oxygen plasma or some other process where some high energy species changes the energy of the polymer from a low state to a higher energy state. It becomes more hydrophilic in nature, and as a result of which it develops some silanol kind of linkages which can condense to each other to formulate a SiO-Si bond, and a water molecule comes out. So, this technique is really some kind of a surface chemical modification, and as pointed out here in the different pressure regimes, it happens towards the high pressure plasma etching regime, because the idea is to be able to just etch away a small portion of the surface chemically, removing the backbone really intact. Okay, that is the whole purpose. So, what really happens in terms of removal? Let us talk about this model system of PDMS, polydimethylsiloxane, which is used in most of the cases for replication and molding techniques. and then later on plasma bonding or clean bonding is used for forming multiple layers or stacks and closed chambers and features. So this is essentially the PDMS species with a double methyl group, as you can see here on the SiO bond. Okay. So use UV excitation and oxygen plasma and create CH2OH group on the surface here. You actually take off the CH2O group off the surface, and it reduces into some kind of a free radical species. This is a dangling bond of silicon which is left over, and there is a lot of OH within the plasma. You have oxygen species. Let us say you have created an oxygen plasma and you are trying to expose the surface. So you have oxygen species, oxygen free radicals, which would react with water vapor and equilibrate with that to formulate a lot of OH with dangling bonds, and this would essentially come and sit on the top. So therefore the methylated surface here of the PDMS really changes to a hydroxylated surface, as you can see here. The effect can be very beautifully observed in terms of a change in what you call an advancing contact angle. So if you put a droplet of liquid over such a surface which is highly methylated, there is always it behaves like a lotus leaf. Okay, it almost always beads up the water into a small football kind of a mechanism, okay, with a very high contact angle, about 108 degrees, about 110 degrees, close to that. Now if you have exposed this surface to oxygen plasma and you have hydroxylated the surface, there is going to be a lot of polar moieties on the surface, and therefore the effect is almost immediately visible. The water droplet here is now kind of no longer beading, it is trying to wet or spread around on the surface. So it shows that the surface has gained energy. Okay, it has definitely changed or modified chemically. So therefore the indication of OH is really made by looking at, indication of the concentration of the OH is really made by looking at the contact angle of the surface. Now my supposition here is that if suppose let us say you have two such species which are formulated these hydroxyl moieties over the surface, and you bring them in close proximity with each other, there is almost a tendency of this SiO-Si linkage to be formulated and a H2 group being generated. Okay. So this is the way things bond together chemically irreversibly. So therefore if you expose two pieces which is methyl rich polymer pieces and then bring it closer to each other, there is a tendency of an irreversible silanol SiO-Si kind of linkage to be developed. Now assuming that is true, the bond strength really then would be a function of how many hydroxyl groups are there on the surface. So if you have more number of, if you have a higher density of the hydroxyl groups, there is almost always a better bondage in terms of sticking to one another at several active sites in comparison to one where the hydroxyls are the concentration is depleted or limited. So here the idea is that can I really develop a common scale of reference to ascertain my plasma treatment or level of plasma treatment, where I can find out or correlate what would be the best possible parameters, plasma parameters used for the maximum bond strength. So this is essentially something that we have reported, our group has reported earlier, where we talk about an universal curve for PDMS or PDMS glass bonding. And here as you are seeing here we measure the bond strengths of several such surfaces after we have exposed them to oxygen plasma, and also parallelly measure their contact angle. So we are very amazed to see that the bond strengths falling in a regime less than 10 degree contact angle on the surface are the maximum. So maybe the number of hydroxyl groups on the surface which causes this water to kind of spread around and wet the surface increase very prominently, okay, resulting in actually a zone here as you can see which is relatively very high bond strength area. So all it needs is to kind of investigate different plasma parameters experimentally and check the contact angle every time, and then alter the parameter in a manner that the contact angle can go below 10 degrees or so. So you are mostly certain that there is a 100% bonding mechanism carried on between the two wafer surfaces if you could actually take it below 10 degrees or so. So this is a very interesting observation that one has from such references. So the way the bond strength can be measured, and that is actually we did in this experiment, and this paper was reported back in 2005 in Journal of Microelectromechanical Systems. Here as you see you have a Pdms blister which is failed, okay, because of the pressure. So a blister essentially is a small embedded chamber inside the two pieces of bonded PDMS with a supply point which is covered with this peak tubing, a steel gauge which takes all the air inside this chamber, and epoxied at the corner here. So this is a total system. The epoxy used in this case is a quick setting less than 5 minutes epoxy, and it creates sufficient bond strength for the epoxy, between the epoxy and the peak on one side and epoxy and the PDMS on the other side, which avoids any kind of failures, etc. And then what we do is we supply compressed air inside at a controlled rate, just thus manually observing the pressure level, and this compressed air goes into this blister and starts expanding the blister till and until we see a separation starting to happen on the edge like this, okay. So there is a separation which has started to happen. Now this separation is essentially determined by a microscope, and then the moment this separation starts taking place, a reading is noted on the compressed air, the gauge for the compressed air, and a pressure level is found out in terms of PSI, which has caused or initiated this separation to happen. It is a very quick process, and this particular PSI level is essentially the internal pressure of the blister. We can calculate what is the pressure on the outside of the blister. It is basically by Pascal's law, it is distributed, okay, and we assume them to be equalized. So the pressure that you read out on the regulator of the compressed air is also the failure pressure for the blister to be disintegrated and the PDMS to be separated from the PDMS. We consider that to be the bond strength, okay. So we consider the amount of pressure at which the blister separation takes place to be a function of the bond strength of the material. So if we assume that, we can find out really that the bond strength is really a function of the several different parameters like time of exposure, plasma pressure, the flow rates, so on and so forth, and the RI power that is being used. And typically we find out that the most favorable systems are also the high pressure low power kind of systems, where there is just a small layer of chemical change which is made on the surface without really going into the siloxane backbone of the material, okay, without really going into the SiO backbone of the material. So therefore it is very desirable to operate the plasma system in a manner that you have a high pressure, extremely high pressure, low mean free path, and low power given on. The idea is to just be able to modify that small metal layer and create several dangling bonds, so that you have interlayer bonding between the two exposed surfaces once they keep together after this exposure is over. So there are several effects that PDMS surface would have on plasma exposure. People have reported this off and on in several materials or several literature sources time and again. In one illustration here, the surface transformation takes place due to the UV of the plasma generating a silanol. In another illustration you can see there is a different scheme of mechanisms which is happening here. You have a metal, you have the metal going out and a dangling bond which is created, and then you have again an adsorption of OOH from the oxygen. Hydrogen is picked up from the water vapor of the atmosphere. Then you have a OH free radical going out now, and then you have a O free radical species generated in Si, and finally you have this O available for any kind of bondage. So there are different schemes by which you can illustrate what kind of surface transformations would take place, and this is basically done on real time basis using spectrometric studies inside the plasma chamber, okay, on a real time basis. So you insert a probe and see what exactly are the transformations, what are the kind of signals which are given, and correlate the bond energies to see what are the intermediate states which are formulated in the plasma as it has been generated, and we are working on striking it onto a surface. What is also very important for me to tell you is that surfaces of polymers normally crack, okay, especially on exposing to these kind of high energy radiations of plasma or ionic gases, and it is very natural to assume that they crack because of the kind of ionic momentum delivery that you give onto the surface. Now assuming that there is a silica layer which is formulated by exposure at the first site and this is the thin silica layer, and you have already formulated cracks here, and you know that the internal structure of a polymer is highly dynamic and there is always a circulation and movement of oligomeric chains inside the network. It is almost always kind of logical to assume that some oozing out of these chains will take place on the surface. Okay. So, with time, if I leave an exposed surface, it should again try to get back its hydrophobicity by these materials trying to ooze out continuously from the crack and going and spreading all over the hydroxylated surface and covering another layer of metal on the top of the surface. Now, these are these oozing chains which are actually going out. The polymer structure itself in its depth is very highly dynamic in nature with things floating around. Okay. That is how the polymers are made of. They have extremely high energies in terms of chain flexibility, the elasticity, etc. So, if you assume that that is the case, and especially the cracks are more prominent if the plasma treatment is harsher, that means if you have high power and lower pressure side, the cracks are more promulgated essentially. So, there would be a severe tendency of surface recovery. Okay. So, the surface energy which has been hired by the exposure would slowly lower down with time just because of this oozing out action and covering of the surface from the internal structure, from the oozing out of the internal structure of the polymer onto the surface. So, assuming that happens, can we really characterize it? The question is that if you use a contact angle, you may be able to find out some explanation. So, these here points out or indicates studies made on another kind of methylated polymer called spin-on glass, which is MSSQ or methyl silsesquioxane, where there is also a lot of methyl rich surface that we have to consider. So, this right here is an illustration of what the contact angle really is before the exposure to oxygen plasma. It is about 83 degrees Celsius, and essentially you try to find out what is the state of contact angle at each time of post exposure recovery by exposing all these pieces together and then covering the others in vacuum sealed environment and immediately measuring after exposure the contact angle. It comes down to, as you see, 7.04 degrees, and then the other sample which was actually exposed parallel with this sample and was kept in vacuum is evaluated after about 5 minutes, and the contact angle comes out to be about 12.75. So, there is a slight increase, that means the surface is trying to recover. It now changes after 1 hour, and this is the third sample which was actually exposed simultaneously with this sample and kept in vacuum. Now, after 1 hour we evaluate the contact angle to be 31.57, and after 3 hours this is 38.67, after 5 hours it is 62, and after 2 days it is about 63. So, you are seeing that the surface contact angle has been recovered to almost about close to about 2/3 or 66% of the initial value of 80, okay, which is amazing actually, 75% I am sorry of the initial value of 80, which is amazing. So, therefore, there is almost a 75% recovery of the surface by means of this oozing action of dynamic chains within the polymeric network, which try to just look for these cracks on the surface and ooze out and form a monolayer on the net surface. Okay. This can also be illustrated separately by and scan on the ATR FTIR, and ATR FTIR is essentially again nothing but attenuated total reflection Fourier transform infrared spectroscopy. So, these right here indicate some of the plots on the ATR FTIR. As you are seeing here, this is essentially corresponding to about 2975 centimeter inverse wave number. This is essentially the SiCH3 bond. Okay. Okay, so let me explain you how an ATR actually works, or an FTIR actually works. So, an FTIR is nothing but a Fourier transform infrared spectroscopy. Okay. What it means is essentially that you have an infrared wavelength which goes into a sample and couples with in terms of photon to phonon conversion or in terms of bond vibration. So, basically the SiCH3, okay, so the way that this FTIR business works is that, as I told you, it is essentially a translation of photon to phonon. So, you are coupling light infrared radiation into a medium, and the bonds of the medium are continuously vibrating because of this light coupling action. And essentially once you basically do this kind of coupling, there is an absorption of a certain energy at a certain frequency or C by lambda, that means a certain wave number. 1 by lambda is actually wave number, that is how you treat. So, wave number based absorption in certain wave numbers happen because of coupling of light to certain bonds which have certain vibrational frequencies, and you can characterize the different types of molecular bonds or environments based on what frequency or what wave number gets coupled to that particular bond. Here for instance, this is the SiCH3 bond, you are coupling light at 2935 centimeter or 2575 centimeter inverse wavelength, and it is giving out a signature of the species, that what kind of bond it is. Here it is SiCH3 bond, it is a signature of SiCH3 bond which happens at lambda inverse equal to 2935 centimeter inverse. So, here you are seeing that the untreated SOG is actually having a pretty high absorption coefficient, which is also dependent on the particular wavelength that you are measuring. So, these are all done at same wavelengths, mind you, because the absorption coefficient changes with wavelength. In this case, the maximum absorption coefficient that you can get in comparison to the different wavelengths that are available for finding out this absorption rate. So, the untreated is at the very top, which indicates that the absorption coefficient is the highest, and so therefore, highest amount of SiCH3 bonds are present really in this particular point. Immediately after treatment, it falls down to this area here, as you are seeing, this is the dotted line. Okay. So, this is immediately after treatment, it falls down, the absorption coefficient falls down, and then 1 hour after the recovery is done, again you find out there is a slow increase in the methylation. So, here the 1 hour plot is essentially this plot. So, from the dotted plot to this continuous plot here, in 1 hour you see there is a slight increase in the methylation peak. For 5 hours again there is a much higher increase in the methylation peak. So, slowly this methyl peak is growing with time, which is also an indication of what is happening on an actual scale. So, ATR, and I forgot to mention this, is basically attenuated total reflection mode. What happens here is that you have a crystal, and this crystal is actually close to the surface in question. So, this is the surface you are planning to investigate. You butt this with the crystal, and then you couple light from outside within the crystal, and in a manner that it gets totally internally reflected and comes out like this. Okay. So, you have this light totally internally reflected, and you can actually do the refractive index variation accordingly. Now, here essentially whatever light falls on this interface between the film and the crystal is responsible for causing absorption losses, okay, of the particular wavelength. Let me write this down a little clearly. Absorption losses of the particular wavelength is almost an immediate effect which comes out. Okay. So, therefore, this right here is an illustration of that the absorption is increasing, which means that more and more metal is generating on this interface, which is causing more and more absorption of the light. So, the outlet frequency here or outlet intensity here is really not really equal to the initial intensity. So, it is equal to I0 e to the power of minus z times of the depth of penetration, alpha times or minus alpha times of z by the Beer's law of absorption, right. This is the depth of penetration, z is the depth of penetration or depth of coupling into this particular medium. So, if alpha is investigated, it gives an indication, or it is basically a direct indication of what is the intensity change. So, we are calculating the I by I0 ratio, where this is I0 and this is I essentially. Okay. This side here is I. So, we are calculating the I by I0 ratio and trying to find out what this alpha value is, the absorption coefficient is, and that you do over different wavelengths, because absorption coefficient also is a function of wavelength. Okay. So, with ATR FTIR I can actually get a feeling of how the metal peak is varying. It is growing certainly. It was initially very high, came down to all time low, and then suddenly growing. Similarly, if I look at the other end, that is SiOH peak formulation, and we are looking here at 3300 centimeter inverse roughly, which is also a good estimate of the SiOH peak in the FTIR scan. You can find out that immediately after treatment, so the untreated sample here has a very low methyl content. Okay, it is at the bottom here, and it doesn't have, it hardly has any symbol. These are all, by the by, these are all kind of normalized over a particular wave number values. Okay, that is how you actually calculate the absorption coefficient here. And when immediately after the treatment is done, this dotted line becomes the new description of the SiOH, which means that there is really a growth. You see the area under the curve here, there is a real growth in the SiOH. The amount of bonds which are available here is very high, and in about 1 hour, again, as you are seeing that slowly the methyl is trying to go on the surface and kind of cover the surface. There is a slow decrease in the hydroxylation of the peak, because this ATR here actually is giving a surface effect. What is going on in the surface? The surface shows that there is a tendency of decrease of the hydroxylation, which means that it is being covered continuously by the oozing out molecules and the diffusion process along the surface. And then again, after about 5 hours, it further comes down and to an all time low of the hydroxyl peak. So, the hydroxyl peak is continuously coming down, methyl peak is going up, and if I actually try to see the area under the curve here. So, here essentially, and these are some arbitrary units in which you are plotting the CH group on this side and maybe the OH group on this other side. So, this curve here really indicates the area under the curve for the different samples, like untreated 1 hour and 5 hour, and this curve here really relates to the area under the curve on the CH group, that is for untreated to 1 hour to 5 hour. And as you see here, the cumulative growth of these areas, okay, or the methyl area is an indication of what is the increase in contact angle. Simultaneously, the cumulative decrease in the hydroxyl peak is also kind of giving a ratio of the contact angles. If you may remember, the contact angles were earlier illustrated here by these different values, and so the ratio of the areas under the peaks is also a clear cut indication of the ratios of the various contact angles with respect to the different time points that has been used for taking this particular data. So, this kind of is an exactly very nicely made estimation of what really goes on the polymer surface, and it is a wonderful characterization technique which tells us the basic science which is going on is essentially a slow or gradual methylation and a simultaneous dehydroxylation in parallel to each other, which makes the surface recover hydrophobicity with time. Now, incidentally, these surfaces can be used for a lot of biological entities, because biological entities itself would tend to de-adhere more to the surface if it is hydrophobic in nature. Of course, there will be non-specific absorption problem which can be passivated by using some other components like BSA, etc. But such kind of films are excellent. We have seen and studied, as I will be demonstrating later in the final lecture of this series, that this hydrophobic recovery of the surface is very positive for minuscule DNA levels also even getting amplified. So, essentially you need to coat the whole chamber's inner walls or interiors with this kind of a film and expose it to plasma and keep it in the open, so it self recovers. And you see that as low as a few nanograms per milliliter, picograms per femtograms per milliliter of DNA solution taken ab initio can also get amplified with PCR or other protocols, especially at the microchip level, just by using this one sole coating. Okay. So, we will discuss some of these illustrations probably towards the last lecture of this particular series. Now, I would just like to summarize the basic various differences between the etch regimes that we have talked about. So, high pressure etching, ion milling and reactive ion etching are the 3 different pressure regimes over which this different kind of etching mechanisms happen. So, high pressure means mean free path of a much smaller size, much lesser than the chamber size. The plasma essentially in this case is used to start and stop chemical reactions. The basic mechanism is by which etching takes place is just chemical. You have a low ion impact energy, again because the amount of free distance available for the ions to move in between before the first collision or second collision is very low. The plasma is homogeneous and isotropic in this particular illustration, whereas in ion milling the mean free path is comparable to the size of the chamber of low pressures, and the plasma is used to abrade the substrate by sputtering out the material. So, essentially it is a physical ablation of the material which is happening in ion plating. Ion impact energy is extremely high and it has a high directionality. So, you have a chance of cutting a very narrow trench, high aspect ratio trench with straight walls in this particular illustration. Reactive ion etching is somewhere in between both the ion milling and high pressure etching in terms of pressure ranges. So, you have a moderate mean free path of the species. Processing is primarily the transformation of the surface, and you have a moderate impact energy of the ions. Degree of anisotropy is definitely higher than the isotropic nature of the high pressure etching, but then is not as high as ion milling, it is somewhere in the center. So, this in a nutshell is the various differences for the different etch regimes that happen that we believe is very important for basic understanding of all plasma processes in the field of MEMS, okay, or MEMS devices. And I would like to kind of go into a different regime of MEMS processing called additive techniques. So, here essentially you are talking about things like chemical vapor deposition to make thin material films on the substrate. So, you have a gas phase and you create a reaction in that gas phase, and whatever is precipitated is actually captured on the top of a surface. So, the gas phase can make SiO2, it can make silicon nitride, it can make silicon carbide, and then you can capture these moieties from the gas phase onto the surface in question, and that way you can develop thin films. And such reactors are also known as CVD or chemical vapor deposition reactors. So, essentially there is a material created inside a reaction inside the gaseous system, and that is captured over the surface in question. So, it is an important technique for creating material films. In a CVD process, the gaseous reactants are introduced in the reaction chamber first. Okay, the reactions occur on heated surfaces resulting in deposition of solid products. Other gaseous reaction products leave the chamber typically, and depending on the reaction conditions, the CVD processes now can be really categorized as atmospheric pressure CVD, APCVD, low pressure CVD, LPCVD, and plasma enhanced chemical vapor deposition PECVD. Okay. So, typically the low and atmospheric pressure CVDs involve elevated temperatures about 500 degrees to 800 degrees for the reactions to be used for depositing films on the substrates. By temperature we mean that the substrate, I mean that the substrate is heated to this particular temperature, so that whatever is happening in the gas phase interacts with the vibrating lattice on the top of a silicon substrate and becomes one integral with it and starts building it, diffuses through sometimes the particular silicon species and makes a thick layer of the particular material that you want to deposit. So, for metals though, sometimes with low eutectic temperatures, let us say gold etc., these temperatures are pretty high. Metals would melt as low as 380 degrees, especially in thin gold films, or aluminum films may melt all the way, it may go up to about 577 degrees, but certainly it cannot take the additional temperature which is used for LP or APCVD processes. So, there is a cold plasma process for that kind of a situation which is normally used, wherein instead of this high temperature lattice vibration effects, you use plasma to create ionic momentum, so that you can deliver what is happening in the gas phase simultaneously by creating a plasma phase over this whole substrate, and let the ionic momentum take care of the embedment of the gaseous product being made onto the surface in question. So, it is actually a cold system where with lower substrate temperatures, typically about 100 to 300 degrees Celsius, you can still get thin oxides or nitrides formulated. Now, this is a very interesting and important process, because in microelectronics or in MEMS, we almost always need to cover material electrodes or metal electrodes with these insulating layers. Okay, and because you have to have separation between the different levels of the architecture, you have to provide adequate insulation between the different levels of architecture. Therefore, one layer of conduits may not be connected to the next layer of conduit which is over it. So, in order to prevent such steps or processes, you have to use some material or some process wherein there is no evaporation issue with the metal conduits which are formulated. So, if you have a case where you at a colder temperature you are able to generate this oxide insulation over the top of this electrode material, that is probably the best that microelectronics or microfabrication could offer to MEMS industry. So therefore, most of the insulating layers on electrodes, especially in multi-level architectures, whether it is microelectronics or MEMS, is done using PCVD methods or plasma enhanced chemical vapor deposition methods. So this right here is such a system. It is a PCVD bought from MV Systems. It is used for a lot of dielectric deposition, surface plasma treatment and other associated processes. You see the chamber in this particular region here, and the associated vacuum pumps, the power sources, the RF signal sources, etc. The gases are actually supplied onto this system externally. There are special pipings which are meant for evacuating the chamber. So there is a separate vacuum circuitry. There are pipings which are meant for flowing different gases. There are mass flow controllers which can control very accurately how many SCCM or standard cubic centimeters per minute of flow is essentially inletted or put into the chamber or made an inlet to the chamber. And also the whole system has a purging mechanism where you can easily control the vacuum at the time of loading or unloading the substrate wafer or the substrate material. So this is a very nice additive technique. Another important technique I have already mentioned is the thermal oxidation. I am not going to go through this. So let us actually do a small example problem for understanding the thermal oxidation process. Here, as you see, the density of silicon and silicon dioxide are 2330 kg per meter cube and 2200 kg per meter cube respectively. Molecular masses of silicon and oxygen are about 28.09 kg per kilomole and 15.99 kg per kilomole respectively, and we want to determine the consumed silicon thickness for the silicon dioxide film thickness of thickness D. Okay. So we assume if the oxide thickness is D by ellipsometric measurements, etc., what is the consumed thickness in turn of the silicon? I just want to recall that this thermal oxidation is a diffusive driven process where there is a tendency of the oxygen atom to come within the lattice and sit and make the oxide layer. So we can solve this by saying that for a 1 kilomole silicon, will get about 1 kilomole of silicon dioxide. Okay, that is how this reaction works in. So you have a unimolar composition of this reaction, 1 mole of silicon reacting with 1 mole of oxygen to produce 1 mole of silicon dioxide. So if this is a kilomole, the yield will be a kilomole. Now assuming that to be true, and we also assume that we are actually having the same surface area to grow the silicon dioxide as you are having the available surface area for silicon. So the area is same. So essentially the volume of silicon that can be found out by multiplying the density of silicon. Okay, so therefore if you compare the densities between the silicon and silicon dioxide, it is essentially so we can say that the densities are mentioned here as 2330 kg per meter cube for silicon and 2200 kg per meter cube for silicon dioxide. Now as we may assume that the area on which the silicon dioxide is growing is essentially same as the area of which the silicon is consumed. Okay, so these areas are same. So assuming that to happen, the thicknesses of the silicon per unit thickness of silicon dioxide is also same as the volume ratio, because the areas are same in both cases, they are all same in both cases. So the volume of silicon to silicon dioxide really determines the thickness of silicon to silicon dioxide. Now I know that this is D. Okay, that is what the question says, that you have a consumed thickness of silicon which is D, and so therefore you can say that the volume here is nothing but the mass per unit density of silicon and mass per unit density of silicon dioxide. So once we do that, we can find out the mass of silicon dioxide from the values of silicon and oxygen independently, which is given here. So there are twice oxygen plus silicon. So this many kgs per kilomole, and this divided by the density would give the volume of silicon dioxide. Similarly, the total amount of mass of silicon is about 28, molecular mass is 28.09 kg per kilomole. So this divided by the density of silicon 2330 kg per meter cube would give the total volume of silicon in this particular case. So the volume ratio is same as this ratio here, as you can see, which comes out to be about 0.44. So, therefore, the total amount of thickness of silicon which is consumed is about 44% of the thickness of silicon dioxide which is created, okay. And that is essentially what the question was, that how much was the consumed silicon thickness. So, with this I would kind of tend to close this area of microfabrication, and next lecture we will be talking on a very interesting area of how this we can integrate these all techniques together to build real biochips or real systems. Thank you.